So what we have done till now, we try to find out the pack parameters, that means pack capacity, voltage, current, and then based upon that we found out what is the weight of the cell, and then we saw the various forces which can act on a battery pack: compression, tension, shear, torsion, bending. And then we understood what is the stress, what is the strain. There was a mistake here, deformation. It should be deformation or displacement, not deformation of displacement. Then we have seen what are the forces acting on a battery pack, and what we have seen, it's a bending force on the end plate, bending force on the base plate, then tension or compression on the side strips, then shear on the bus bar or in between the cells. And then we have started thinking about what would be the base plate dimensions and thickness which can take the required load. So what we found out, that we already know the length and the breadth of the base plate by virtue of setting up 2 modules, knowing the cell's dimensions, providing the sufficient clearance between the cells and between the modules. And then we assumed we have some of the assumptions. It's the plate is continuous rectangular plate with a constant thickness. It is simply supported at all the edges, and the weight is distributed uniformly over the plate. And from that we found out, we already know length and breadth, but we don't know the thickness. So to find out the thickness, first we found out what is the load, and that load turns out to be 2.554 into 10 to the power 3 Pascal, or 2.554 into 10 to the power minus 3 Newton per mm square. Since now we have the dimensions of length and breadth, we don't know the thickness, but what would be the material? There are thousands of material available. So is there any methodology to find out what would be the best material for that particular application? That means base plate. And there is a very nice methodology by Mr. S-Bay, and known as S-Bay methodology. I'll go through this methodology. I'll try to explain it to you, and it's one of the nicest methodology to find out what could be the best material. It has the different stages. The first one is translation. The translation is, what is your objective? You defined an objective function. What is your objective here? One can have different objectives, like one can have my weight should be minimum. One can have that cost of material should be minimum. Weight doesn't matter. One would require both cost as well as weight should be minimum. Somebody else, neither weight nor cost matters, it only matters strength of the material. And when I say strength of the material, what force is acting on the base plate is the bending force. In that, bending strength should be the maximum. One can have that it should run or it should last long. That means ineffective type of loading. Even in that case, it should run for a defined cycles. One can have all those things together. So you have to define your objective functions from the fundamentals, from the stress strain theory, from the loading equations. You may have to solve the differential equation. If you don't want to do that, then you have to find out an analytical solution of that and then utilize that analytical solution for defining your objective function. So that's being done in the translation. Then you have screening. When I say screening, it could be again a multiple way. One of that is what would be the boundary condition. Because you have defined your objective function, but then you also have to put the boundary condition. My cost should be varying between 10 rupees per kg to 20 rupees per kg. In between that only it should be. So that's the boundary condition. So that's your screening out. If you are selecting a material, you are screening out any material which costs more than 20 rupees, I will not take. Otherwise, there would be infinite number of iteration. You will have infinite numbers of results which you don't want. So you screen out. If any material has a density more than this, I will not consider. Only these materials are available, so I don't worry about any other material. So these are becomes the part of screening. There you screen, you try to reduce the number of variables or number of boundary conditions. Now once you have done the screening, then from the objective functions what you have defined, from that objective function you select the ranking of the material. Now you have put the material properties and all other things what you have put in the objective function. From that you select what will be the rank. So it could be that translation, whatever the objective function we have put upon, can be maximization problem or minimization problem, or coupled of both. So what I require to minimize the cost, I can also require minimize the weight. I can also, in the same problem, I also want maximize the strength or ability to hold the bending load. So either it would be a maximization problem or it would be a minimization problem, or it could be combination of this both together. So based upon that objective function's output, by putting the boundary condition and then solving that equation, you rank all the materials, and that is what is known as ranking. Rank 1, rank 2, rank 3, rank 4, like that. Then the fourth one is supporting information. So it's like a byproduct. Now if it is giving you 2 best material out of 20 materials. Now out of 2 or 3, which material you should select? So you can also look upon the byproduct or additional information. Are you looking it for insulation, or are you looking for a conductivity, or are you looking for a corrosion resistant? Now once you have all this information, out of that 1, 2, 3, you can select 1 or 2 or 3 depending upon this the extra information. It might be possible that first, second, third, all 3 are of the similar level or of the same ranking. But then when you need to eliminate, then you use this extra information to select 1 or 2. So nice methodology. So this process helps us to filter out material that are chosen initially. So initially you may have hundreds of material, and then you while filtering out or during screening, you have already objective functions defined. During the screening, it might reduce it. You simply discard. Okay, I don't want this. I don't want this. I don't want this because of this criteria. And then you have a 20 suitable material out of 100. Now you have come to 20 suitable material. Now those 20 suitable material, now you start ranking using the objective function. So most of them will get eliminated with the ranking itself. Now whatever is left out, if it is only one left out which stands out with all other material, yes, obviously you would like to go. But let's suppose you have an option of 2 or 3 or 4 materials in the ranking matrix. Then you use extra information. What else also is required other than your primary objective? What is your secondary objective? And use that to filter out to 1 or 2. And that's how the ASWE methodology works. So a small example here, for our flat plate, that bottom plate, the objective matrix becomes m equal to e to the power 1 by 3, and this e to the power 1 by 3 has come again from the strength. If you solve that equation, it will come from that. Cost of material and density of the material. And what is our objective? Thickness should be minimum. If you see, what we don't know is the thickness, and I don't want very thick. And for that, I am maximizing this function. The maximizing function is m equal to e to the power 1 by 3 cost of material into density. M is nothing but material index. So from this material index, we will look for ranking. And screening, out of 40-50 materials, I have only selected 2. Mild steel and aluminum 6061. Now we are calculating, so that's how we did the screening. Now from this material index, after filling all those values of the material here, material properties here, what we see, these are the material properties, density of the material, Young's modulus and the cost. These are the 3 variables here. Young's modulus and the density is related to the thickness. Cost, I want my whole base plate cost to be minimum. So my material index or turns out to be 21.8 into 10 to the power minus 3, and for that is for mild steel, and for aluminum it's a 5.34 into 10 to the power minus 3. What I see here in the ranking, since my problem is maximize m, so what is the maximum here out of these 2? Out of these 2, the maximum value is given by mild steel. It's 5 times, almost 4 to 5 times of the aluminum 60. So which material we will select? We will select mild steel. Now let's suppose this aluminum would have been around 20 or 18. Which material we would have selected? We don't know. Whatever the function what we have decided, with that it's very difficult to find out which one I should select. Then I'll start using support information. What is the benefit of using aluminum? What is my secondary function? Do I require high conductivity for more heat dissipation? I'll use aluminum in that case. I'll not use mild steel, even though it's a slightly higher ranking. But the secondary objective function, what it says, that you need to dissipate the heat much faster, and that's where thermal conductivity of aluminum comes in picture. So that becomes one more function, one more variable in the objective function, which we have not put initially. If the material index is comparable or material ranking is comparable, then we start looking for the secondary functions. If my heat dissipation itself would have been objective, I would have put it in the primary function. The heat dissipation is not my main objective, it's a secondary objective. So that's why once I found out the material index is almost same, ranking is almost same, then I started looking for the secondary objectives. There is too much difference, almost 4 times. So I am not worrying about my secondary function. So what I'll select here? I'll select mild steel. Now once I have selected the mild steel, I know all other properties of the mild steel. What is the Young's modulus? 200 GPa, maximum yield strength 350 MPa, megapascal, gigapascal, and the Poisson's ratio 0.3. Now I need these 3 information to find out the thickness of my base plate, and then I'll also use analytical solution. I can solve the differential equation for that, and that's nothing but Kirchhoff's equation, and find out all the thing. Or there is already analytical solutions are available. there is something known as design data book. So you take that design data book, you have the boundary conditions, you have the loading pattern, and from that you find out the equation and utilize this information and then your dimensional information and then find out the thickness. It's much easier than solving a second order differential equation. So that's what I have done. So what we have selected here, I have selected a material mild steel. Now we'll go back to the base plate calculation. That's where we have started, and then it came that which material we should select. Now we have selected the material. Now we'll start the calculation of base plate thickness. So Kirchhoff equations for bending in plate, and we have from the Rook's formula for Rook's design book is there. From that we have a formula for stress and strain, and that's a rectangular plate. So you in this design book, design data book, you will have all types of loading and corresponding solution. So you have to find where your problem suits most. So what we have, a rectangular plate of A length and B width, simply supported at all the edges. That's already there, which we have defined. And for that, the max stress is beta cube B square by T square, and the maximum deflection minus alpha q B to the power 4 E, that is nothing but Young's modulus T to the power cube. And at the center of long side, that R max is gamma cube. We will not use this one. Now, what are the things you have? You have alpha, you have a beta, you have loading, you know the width. What you don't know is T square, or basically what you don't know is T. So let's move. So first what we have to find out is this is the A by B ratio here given. For each A by B ratio, you have a constants alpha, beta and gamma. So you have to find out the alpha, beta and gamma. So in our case, the A is 285 mm, B is 138 mm. So what A by B ratio we have got is 2.06. What we have is 1.0, 1.2, 1.4, 1.6, 1.8, 2, 3, 4, 5. So 2.0 where it falls? It falls almost at the 2. Or we can interpolate in between 2 and 3 and exactly can find out at 2.06. But for our sake here, what we have considered, it's almost equal to 2. So now as soon as I know 2 here, now I know alpha value. Alpha value is 0.1110, and then I also know the beta value 0.6102. So I know beta value here, I know alpha value here, I know Q. Q is nothing but the load, which we have calculated in the a slide earlier. What we don't know is T. So let's calculate maximum deflection first. We have put all these values here. Now, when I say maximum deflection, now it depends upon us what is the allowable deflection I should put upon, which is not going to harm anything else. So that we can either assume, reiterate, keep on reiterating unless we find a satisfactory solution, or from the experience, from the past experience, we select a value that yes, I don't require any deflection more than this. And then what we have assumed is this Y max should be 1 mm, not more than 1 mm. And Y max, I am saying you, in such plate, this would, when you are putting a bending, this would come like shape like this. So this is the maximum deflection here. At the center point of this plate will come maximum deflection, and that maximum deflection should not be more than 1 mm. and that has come from either from the past experience, or we have put a value, we keep on iterating what would be the best thing for us. Now, as soon as we have assumed this 1 mm max deflection, then from that, now we can calculate T, and that is cube root of all other values here. What we have found is coming around 0.788 into 10 to the power minus 3 meter. It's nothing but 0.8 mm. Now, you may not have 0.8 mm plate available, or you wanted to put a factor of safety, then you will go for a higher size, higher thickness. So, what we have done here is we have selected a 1 mm plate. Now, once we have selected a 1 mm plate, then we need to find out what is the maximum stress which can happen into the plate, and that should not be more than the allowable stress of the plate. That value also we have maximum stress of the plate, the yield stress also available there. So now, from the formula of the max stress, what we have found out, that the maximum stress which can develop by a 1 mm plate is 29.6 megapascal. If you see the material properties, what is our maximum yield strength is 350 megapascal. What we are getting is approximately 30 megapascal. So, it's much less than the yield strength. So, my material is not going to fail. But what we have considered till now is only the weight of the battery pack. We have not considered any other force. There could be many other forces. When the battery pack is fitted into the vehicle and it's running on the load, you may encounter different forces. So, once you have done this iteration, you have to come back. You have to find out, is there any other force acting on that? And then you keep on iterating till the time your all the force calculation get satisfied. Now, we have selected 1 mm. Somebody can select even 0.5 mm. He may not have a luxury to go to 1 mm. In that case, this all the calculation, all the values will change. Calculation remains same, values will change. Now, when we are selecting the 1 mm plate, what was the design calculation is 0.8 mm, and we wanted to put a factor of safety, or 0.8 mm. If it is not available, then 1 mm. The nearest available solution is 1 mm. It could be on lower side also, but then you need to work out, because in this case my sigma max is very low. I can even go to lower side also. I can go even to 0.6 mm if it is available, and then we recalculate back everything together. In that case, my deflection would come more than 1 mm. Is it acceptable or not? If that material is easily available, it's a very cheap, and if I say no, even 1.2 mm deflection is okay for me, or 1.3, whatever comes from that, then we can go even for that selection, because my sigma max would still be satisfied. So, if you have selected a plate of 1 mm thick, in that case my maximum deflection would be only 0.8 mm, less than what we assumed initially based upon experience or the design criteria. Any question till now? Fine. So, what we have done is we have shown you a sample of base plate forces and thickness calculation. The same way you can do for the end plate, you can do for the side strips and inner casing, outer casing, everything. And this would be, obviously it would be a long calculation process, but this is what you have to start with. Once you have done this one, You can automate that thing, you can put it into the Excel sheet. Next time when you're doing, you're just changing the values and all the things will come out from that. But as a first step, you should start doing in this way. The next what I am going to talk about is battery swelling. What happens in the battery swelling? And this phenomenon is, when I say swelling, contraction and expansion. It's mostly expansion, and this phenomenon mostly happens in pouch cells and prismatic cells. In cylindrical cells, by virtue of its design, it does not happen more. So why it happens? If a pouch cell, if you overcharge, because of the release of heat and that gaseous, it can swell like this, because you don't have any constraint outside. It's a soft material. So what it will do? Even application of a small internal force, it will start swelling up. Any defect inside the cell, and it's impossible to have zero defect. Might be 1 in million, might be 1 in 10 million, but this can happen. Mechanical damage to the electrode during the transportation or by some blunt force. If you just drop the box, cell box, or on the assembly line, some blunt object has hit the cell. Because of that, it can happen. If the cell is kept in excessive temperatures, 70 degree, 80 degree, 90 degree, 45 degree, you know, our cells are base designed for 15 to 35 degree centigrade. In such cases, in all those cases, it is possible, or during the deep discharge, so overcharge and during the deep discharge of the cell. So some toxic gases, or you say simply gases, forms up, and because of that it swells. What happens in the prismatic cells? Difference in temperature gradient across the surface can lead to uneven expansion and contraction, either during the charge, discharge, or deep discharge, fast charge, and all the things can happen. And this induces a thermal stress, because now you don't have a cylindrical surface. What you have? The corner you have more stiffness, at the center you have less stiffness, it's try to bulge out at the center. Now as soon as this happens, it impacts the cell life drastically. You don't want it to happen. Since you don't have a control over manufacturing, you don't have much control over charge and discharge also, because once you design, this is the charge side, this is the charging rate, and this is the discharging rate, it will keep on happening. Anything beyond that, only BMS will cut off. But still in such cases it can happen if it is not constrained properly. So what one need to do is to constrain the cell in such a way that this expansion or contraction should not take place. In the case of pouch cell, in the case of prismatic cells, the bulging of the cell should not take place by providing the sufficient constraints. And how can I provide the sufficient constraint? By external means. And that's where the end plates comes into the picture. When we design a module, or when we design a battery pack with the prismatic cells or pouch cells, we always have constraint on all the surfaces. Okay? Any question till now?